Good morning. So, what we are going to do today is I realized that yesterday's last task, the tutorial part, there are still some confusions. Some people were not able to solve it. So, I'm going to spend some time on that review. Then we'll take a look at the resilient modulus models today again, and then try to see what are the model parameters, what do they signify and stuff like that. And then we will go into permanent deformation, which is rutting and rutting models. We will again look at a rutting model determination and stuff. And then for the tutorial today, there are a couple of things. The rutting model rutting model fitting is very easy. We don't need to spend much time on that, but we will look at some DCP data and some lightweight deflectometer data and of how the subgrade characterization works and stuff. And if time permits, I may do a little bit of something like an illipave or something today, because the plan for tomorrow, uh, based on the discussions for the first 3 days, I think one of the areas that you will gain more from is if we go into a little bit of uh, what kind of instrumentation gets used to measure what in the field and how that data is useful as we make inferences about it. So tomorrow I am hoping to spend pretty much the entire day on talking about different projects with sensors and what the sensors give and how you can use the sensor data to make sense of different things. So we'll see. That's the plan. Again, it can evolve based on discussions. Sorry about my voice again. It's starting to get bad. Hopefully I survive tomorrow, and then I don't care. Uh, so let's start this. What I'm going to do today is so December 12, 2024. Okay, and is it visible clearly? Okay. So what we can do is let's look at the MR models again. So the the first one we're going to look at is the K theta model, right? And so the formulation is K theta raised to the power n, where theta is the bulk stress, and that is sigma 1 plus sigma 2 plus sigma 3, and that is bulk stress. And K and N are model parameters. And for dimensional consistency, we write MR is equal to K theta over P0 raised to the power n, where P0 is equal to 1 kPa or 1 psi, anything. It's basically unit pressure. You are just trying to make it dimensionally consistent, right? So what we are trying to do, there was one question that I had yesterday, is in our laboratory test data that I shared with you. The question I had is, where do the models come into picture in that test data, right? The answer is nowhere. The models have nothing to do with your test results. Testing is just to determine properties of the materials. Model running so that you can mathematically represent that test. There is no obligation for you to fit a model to a test. Is that clear? You don't have to fit a model at all. So where do K, N, K1, K2, K3 come into in the test file? Nowhere. right? So that's something you have to be very clear about. Model, you are only, it is quite possible that you can spend your entire life only running tests and not fitting a single model, if that's what your objective is, right? So your test data will not give you any of these parameters. The parameters are needed because you are going to do some calculation for which you want to represent MR as a function of stress state. That's basically the whole purpose, right? So how do you do this? So let's just say uh, somebody pull up on your laptop the columns you have on the test data. Any with a laptop, but just open, because I don't remember. So if you go to that test data, we had, I think the first one was sequence. Second, I think, is called pulse group. Then we had axial base stress. Then we have axial deviator stress. Then I think we have radial base. Then we have radial deviator. Then I think axial resilient deformation, one axial resilient deformation, two, and several others, which honestly we don't use in this exercise at all. Let's people who had difficulty, please fitting that, please make sure you take notes and stuff, because I don't want you to leave this class not knowing how to fit a model, because this is probably one of the most important ones. The sequence here starts from 0, and if you see, there is a 15 as well, but that 15, if you look at the stress states, is actually pretty value. It's basically a test ending protocol, so it's not an official stress sequence. So you only care about 0 to 14, which is the 15 stress states, right? So this 15 in your file you can ignore. You don't have to do anything, okay? Because resilient modulus test, we said there are 15 stress sequences, right? So 0 to 14 is 15 stress sequence. Then pulse group, for everything we had 1, 2, 3, 4 pulse groups, okay? What I said is the a resilient modulus test, for every stress sequence you have 100 pulses per sequence. Because this is a research equipment, what it does is 1 to 25 it merges into pulse group 1, 26 to 50 is 2, 51 to 75 3, 76 to 100 is 4. What did I say ASTO T307 does? It takes the last 6 cycles and then takes an average. In this machine, you don't get last 5, you get last 25. So you just have to use that. That's basically what it is. Okay. So what I'm trying to say is you are doing this 76 to 100. So this is the pulse group of interest for you, right? Okay. So now you have 15 stress sequences. So in your Excel file, you delete 1, 2, 3 stress sequence for all the 1, 2, 3 pulse groups for all the stress sequences. So in the end, what do you end up with is 0, 1 all the way to 14. So this is your sequence, and then this is your pulse group. You'll have 4, 4, 4 all the way to 4. Does that make sense? Okay, Those who got it yesterday or were able to do it, you saying yes does not mean anything to me. I want yes from the others who were not, because I don't want this to end this class without that. So 4 is all we're doing, right? Now let's go step by step. So this is the University of Illinois fast cell, and what I said is there is independent control over the vertical and horizontal. So what you have here is sigma V0, sigma Vd, sigma H0, sigma Hd. That is how you are controlling the stress state here, right? You are independently applying the confinings, independently applying the deviators. So what does that mean? So this in your data sheet, this is axial base stress. This is axial deviator stress. This is radial base stress, and this is radial deviator stress. Make sense? That is what your stress sequence or stress meanings are, nomenclature. So sigma V is equal to sigma V0 plus sigma V d, right? And sigma H is equal to sigma H0. It would have been plus sigma Hd if we were pulsing in the horizontal direction as well, right? In this case we are not. So what I am going to do is I am going to write sigma Hd, but I am going to circle this and I am going to say this is 0 because vertical pulsing only. That makes sense? Why do you have little values in there? That's because it's just sensor. It's sometimes sensors garbage and stuff. You just have to ignore that. So now you have, and because it's a triaxial test, we can replace the V and H with 1 and 3, right? Major principle, minor principle. So sigma 1 in this case is equal to sigma V0 plus sigma Vd is equal to sigma V, and sigma 3 is sigma H0, right? So now what you have is, that's the stress. Let's take a look at the definition of MR. What is MR? MR is sigma d over epsilon r, or recoverable strain, not deformation, strain. In your data file you are given axial resilient deformation 1 and axial resilient deformation 2. You are given those because there are 2 LVDTs. If you compare the data, and this is what you should do when you are running a test as a researcher or something, when you compare the data you will see they are not identical. That basically means the system is not really always moving exactly vertically. Again, that is granular material test, that is how it is. If it's exactly identical, you can actually question the data. There's something weird happening. So aggregates don't behave like plastic or something, right? So what you're going to do is take average and to determine average axial deformation. Then epsilon r is nothing but delta average r divided by specimen height, which is 150 millimeter in this case. Yes. So now what do you have? If your table, if you now want to take draw your table again, I know I am doing this repetitively because I just want to get it in your brains. So sequence number, pulse group, now we can eliminate because it's only 4, right? Every pulse group is the same, there is no difference in there. So I'm going to eliminate that column. I'm now going to say sigma V0, sigma Vd, sigma V, sigma H0, and then now I have epsilon r average, right? We just calculated all of that. So if you do, let's just say sequence number 0, and I'm going to just write it in PSI just so that my hand calculations make sense. So your sigma B0 should be 3, this should be 3, this is becomes 6, this should also be 3, and then epsilon r is something xxx. So then your MR becomes sigma vertical deviator divided by epsilon r. So sigma vertical deviator divided by epsilon r. Yes, this is your first check. These numbers should match what the software is already giving you, and we did it and it matched, right? So now you have your data. So is the data reduction part clear? Yes. Now we go into, so this is test results. Again, I want to highlight, your test results have no implication to your model. If you want to fit the model, that's different because you want to do something else. Your test is your test. So now the question is, now you are trying to go and fit models. What are you going to do? Let's just do the k theta model first. So I said MR is equal to k theta over p naught raised to the power n. We are now going to fit this model. There are many ways you can do this. You can actually plot MR against theta and exponential, not a power curve on Excel. It will directly give you this. It does. You can try it. It's very simple. But the point is that does not teach you how to do it manually. So what we already always do is log MR is equal to log K plus n log theta over P naught. So, and we said this is of the form Y is equal to, this is C, this is M, and this is X. So this is of the form Y is equal to mx plus c. So if you now just take a random graph, plot log theta over p naught, which is basically theta, I just write theta over p naught to be consistent, and you plot log mr, you will get a line like this. This intercept is what? Log k, and this slope is n. So you directly get your n. You don't get k directly. You have to take your intercept. So intercept is equal to log k. So that means k is equal to 10 raised to the power intercept, because I am doing base 10 log, I am doing normal log, and n you get directly. So then you can write your model as mr is equal to k theta over p naught raised to the power n, and you just obtain the two numbers. That makes sense what we just did? It's just a matter of plotting the graph, and then you can check. Pushpak, did you realize where you made a mistake or something? Because you said you're getting some weird values. Maybe we can take. No, we don't need to. As long as all your units are the same, it doesn't matter. I wrote PSI because that's the numbers I remember. If you delete it and make it KPA, I don't care. I mean, if that makes you happy, I can actually change this. I'll just make it KPA, and I think I'll just. I don't remember it. Does anybody remember values from anybody who finished the model? Okay. That's what you got. Okay. I don't remember, honestly. I honestly don't remember. I can run it on my MATLAB code and take a quick look. Uh, yeah, 0.56529354.55, right? So that's what you should be. So if you're not, then check your numbers. Maybe you didn't eliminate the last stress state or something like that. That's probably what happened. The 15 needs to be eliminated. But anyway, is the procedure clear for everybody, what we're trying to do? Now, the next model is the Uzan. If you want to go into Uzan, the formulation becomes MR is equal to K1 theta over P0 raised to the power K2 sigma D raised to the power K3. Now it becomes a little bit complicated to directly fit a power curve or something, because it's a multivariate problem now. But the good news is you can do multiple linear regression in Excel very easily. You can still do log MR is equal to log K1 plus K2 log theta over P naught plus K3 log sigma D. Actually, it should be P naught as well. And then you do what is known as multiple linear regression. By the way, one thing I give you some idea. Education in your time right now and research, I mean research my time as well, because I'm still a researcher, right? I'm not in school, but I learn every day, has become extremely easy with the tools like ChatGPT and stuff like that. Make good use of it. You know, people think it can only be used plagiarism. The answer is no. It can actually be used to educate yourself a lot, right? I learn, I would say 75% of my coding from ChatGPT. If I'm trying to do something, I would just say, okay, give me a code to do this, and then I take it and then I modify it and then I do the things. There is no point in reinventing the wheel and stuff like that. So if you don't know how to do multiple linear regression, yes, these are things you can even find YouTube videos, but just type in ChatGPT, it will teach you how to run this thing, how to model fit in Python. It will actually teach you do that. That's basically how you build skills, folks. Not for everything, at least especially researchers. If you rely on courses to learn everything, then you'll be taking your entire life. You'll presentation. You have to teach yourself things, right? And that basically, like when it was COVID time, I actually, because the schedules were wrong, that's actually the period I actually sat down and taught myself how to code R and how to code in Python. I had never touched my entire life. I've been a MATLAB coder. I didn't know what Python was, and I was a SAS coder for statistics. I do SAS programming, but then I taught myself the whole thing. I would just watch YouTube videos. NPTEL. I'm sure everybody knows what NPTEL is. In my research group, when students join, the first thing I do is I pull up NPTEL web. I said, this is what India is doing. Go. You guys are not using it is very embarrassing. If you are not, you should, right? Make good use of it. I mean, there is actually a professor in IIT Kanpur. He does a lot of statistics teaching. I actually took, like, during COVID, like 4 of his classes, and that's how I taught myself the entire R coding and everything. If you want to learn, there are pavement design classes. There is everything is there. Everything is there. So just make sure you do that. Scroll up. Which way? This? That's it. Okay. So if you don't know what to do with the code and stuff, just use ChatGPT. In fact, you can. I don't know how much you all have played. How many of you have played with ChatGPT extensively? It can do everything. I have copy pasted blocks of code and asked, what does this code do, and it explains what it does. That's how you interpret code as well. So if you take my MATLAB code and you have no idea, just copy paste it and say, what does it do? Tell me. And it will tell you that this is what it's doing. It's very, very useful, folks. Just make good use of it. Self-learning is the best learning. I mean, people can only give you directions. The very last one is MEPDG, or the universal model. That's MR is equal to K1 PA theta over PA raised to the power K2 tau octahedral over PA plus 1 raised to the power K3. Exact same thing. Linearize, fit the multiple regression. You just have to keep track of what your intercepts are. You can't do blindly. You can't jump. So if you log MR, log K1, well, it's probably easier to do this. I think because MR is a value and PA is 101.7 or whatever you want to take, like depending on KPA or PSI, I would say just divide the PA directly over MR because it's a value. It's going to make your life much easier. So log MR over PA is equal to log K1 plus K2 log theta over PA plus K3 log tau octahedral over PA plus 1. Just have to plot, just have to determine this is the y variable, this is x1, this is x2. x2 is not a ratio anymore, it has a plus 1 in it as well. Just make sure you add it and you fit the model. Then you get your slopes. Again, intercept is log K1, not K1 directly. Slope number 1 is K2, slope number 2 is K3. That's pretty much it. Does that help? Do you think you can finish this now? Yes, if you just follow this, it should be straightforward. Because we are on the topic, let's visit a little bit one thing here. Let's take a look at the, we said granular materials are stress hardening and uh, sub, and the most common way of modeling them in the past was for granular materials. It is usually the K theta model, right? It's the bulk stress model, or it's a helping. It helps, it captures the hardening really nicely. And for subgrade soils or fine grained, it was actually the bilinear model. What is the bilinear model? It basically is this. So you plot it against sigma d. This is MR. You have a first linear component, second linear component, and you can K1, K2, K3, K4. There are 4 values, and you can just do. But the point is, when you are trying to do any modeling, right? What are you going to use? You don't have. What if there is a mixture of materials? What if it's an aggregate and a soil mixed? How do you isolate them separately, right? That is the reason they came up with the universal model, right? The one model, MEPDG. MEPDG is not for aggregates only. MEPDG is not for soils only. MEPDG is unbound materials, complete. Okay? So what it does, and it's basically the Uzan model, like a modified Uzan model. But if you look at it, MR, K1, PA, theta over PA, K2, tau octahedral over PA plus 1, K3. And what did I say tau octahedral was for a cylindrical triaxial? Anybody remembers? Square root over 2 over 3 sigma d. So it's basically a constant times sigma d, right? So that's why I say it's a modified Uzan method, because it's basically like a sigma d plus 1 kind of a formulation. Constants will just play certain roles in there. Your coefficients are different. For aggregate materials, stress portion that actually represents the stress hardening properties. For subgrade soils, it is the K3 portion that actually represents the stress softening. So what can you say about the sign SIGN, not SINE, sign SIGN of K2 and K3? K3 will be negative because it has to pull the value down, right? So your K3 values are always negative because it is the stress softening behavior that it models. Okay? Whereas K2 is the hardening behavior. K1 is an overall property, basically. It's always a big value. It's dependent on stresses and stuff like that, properties and stuff. So now the question becomes, so I wanted to address this because at least for the master's students and stuff, I don't want to leave a gap by saying that, okay, model, right? Why these models? The objective is that we are trying to capture the stress dependence of these materials, and we are trying to predict what the modulus is going to be if we know the stress states. Okay, now you will see that even in MEPDG, like the mechanistic empirical pavement design guide. The forward analysis, or the, for how I said it's not really a design, it's basically analysis and performance prediction. So the analysis part is done by what is known as a multi-layer elastic formulation or layered elastic theory, which is what your IIT PAVE is, which is what MinLayer is, Wesley is, there's many, Chevron is, all of them. It's the same thing, similar concepts. So even in MEPDG, it's actually a layered elastic formulation called Win-Julia. Okay, Win stands for Windows, Julia stands for Jacob Uzan layered elastic analysis. Jacob Uzan, Israel, the scientist I told you, it's his writing. He developed the program. It's called Win-Julia, or sometimes people write it Julia because in Israel it's not Jacob, it's Yaqub, right? Yaqub, so it's Y. So Win-Julia is the underlying code for MEPDG. So what is it? It is a layered elastic program. What is the property of a layered elastic, or what is the main characteristic of a layered elastic program? It has multiple layers, and it is an elastic analysis, and the E value is constant per layer, right? What does that mean? Every layer has, the base has one modulus, the asphalt has one modulus, the subgrade has one modulus. So the question is, I spent all this time to teach you all this stress dependency and everything, and now I am telling you that we are not using. That's actually true, because when you, to represent a truly stress dependent material behavior in a pavement analysis, you have to go into finite element analysis. Otherwise, you cannot assign varying properties within a layer. FEM is very easy. It's every node has a different properties and stuff, right? You can assign that. But if you run a pavement over 20 years with traffic, with climate under FEM, take you 5 hours to run, 6 hours to run, right? That is the reason MEPDG, the trial version of the software came. There was actually a version that came with the finite element part built into it, and it was just prohibitively long to run. So that is the reason they eliminated it. Now it's a layered elastic program. So we are actually not capturing what is known as level 1 inputs for subgrade soils and aggregates in MEPDG. It's still level 2 and stuff, because we are not doing true stress dependency in there, at least as of now. There is plans to make that improvement, but it's not there yet, right? So now the question becomes, what should you do? Let's just say that you are now a researcher. This is a question for all the students doing research and stuff. Now I'm doing layered elastic theory or layered elastic analysis, and I am giving you some kind of a layered elastic program. I'm going to only draw the aggregate. Asphalt is on top, and I'm saying you are going to use only one E, but you have a lot of test results already to do this, to support that. Oh, I have the ability to capture stress dependence. I have the model, I have everything, but I don't have the analysis software to do this. How would you, what is your poor man's approach to somehow represent stress dependency in this? Who can tell me? Do you understand the question? So you have the software is able to take only one modulus per layer, but you know that modulus change within this layer. It should, right? But your software is not capable of doing that. What's your poor man's way? How can you cheat the system? You can sublayer right? You can sub-layer because your layered elastic system says and now you can do E1, 1, E1, 2, E1, 3, E1, 4 and stuff like that. And then you can change the modulus in there. Near the surface, the aggregate is going to be stronger, assign a higher modulus there. Below that, it can be lower. Slowly do that, right? Then the question comes is, can you do, yesterday I told you something called anisotropy as well, right? Standard finite element codes cannot capture that. Standard ones, they cannot. There are special finite element codes. One was actually developed by my PhD advisor. It's called GT PAVE or Georgia-Tech PAVE. It's not any more public, but there you had the ability to model anisotropic layer behavior as well. PAVE or anything else, you constantly come across. I think, if I'm not wrong, there is one out of I think Minlayer is layered elastic. There is another one that actually does MICH-PAVE. MICH-PAVE is a finite element thing. It's a code. But again, you can only do so much and stuff. Okay. Before we move on from resilient modulus, there is another thing that one of you asked me. You asked me, I think, yes. Is about, he said NCHRP says to 7th sequence or something like that is what he said. So let's address that. What he meant is, I ran an MR for a soil, MR for an aggregate or something. I have sequence 1 all the way to 15, and I have MR 1 all the way to 15. So I have 15 different MR values from a single test for this material. And now somebody comes and says, hey, what is the resilient modulus of this material? The true answer is yes, it depends. It depends on the stress. If somebody says, still give me one number, I want you to give me one number. Okay. For that, there is something called representative modulus. And people have come up with an idea. HRPs, I think another document, they say that you take the 6th stress sequence out of the 15, and then take that value and report that one. Okay. Why they came up with, there are different theories. I will tell you something which is a much more robust way of doing this. Okay, and you will see how you can do that. Let us assume that you have access to a software like PAVE. Okay, so it is stress dependent modulus. Okay, either today or tomorrow I'll show you the software, how it works and everything. We'll look at it. It can address stress dependent modulus. Okay. Now let's think of a way you can come up with one modulus value, and we have discussed everything for you to have this, and you may have to write this down with me so that you follow what it is going. Let's say we take a representative pavement, right? We take a pavement. So let's say it is something like this. So HMA, ag base, and subgrade is say 4 inches, 4 inches, 12 inches, and this is infinite. Okay, and let us say that you tested this material in your lab already, like this file that you work. That's, let's just say that is your material. Okay, so you now know the k theta values and stuff, k and n values. You know this because you have already tested it in the lab. Okay, what you can do is the following. You take this model, the parameters, like model parameters and everything, and then you put it into a software like Illipave. And you know what you do? You predict or calculate, let's not do predict, let's say compute surface deflection as D0, D8, D12, D24, D36, all the way, like D60 or whatever, just like FWD. We have talked about FWD, so you know that, right? So you can do this. And what properties are being used to predict this? Actual stress dependent properties, because Illipave is 100% capable of capturing stress dependency, right? So you do that. Then you know what you do? You take this surface deflection and then plug them into a back calculation code, just like the one we did here, right? And then you can calculate E1, E2, E3 and everything. Do you see what I just did? I took a stress dependent modulus model, I predicted surface deflections, and I fed it into an FWD algorithm or back calculation algorithm, and now I ended up with one modulus, E2. So that E2 is representative of the entire stress dependent behavior of the entire layer, because that is what you fed into it, right? So this is kind of a cheating or a way around, not cheating, this is kind of a smarter way. Take a complete stress dependent data set and resolve it into one modulus, because the response of a layer with this one modulus is equivalent to the response of the layer which was stress dependent property, because that is how you matched the surface deflection, right? So this phenomenon is called representative modulus. This E2 now becomes the representative modulus. And if some PhD student or some postdoc is looking for a research topic or something, I would say develop a code to couple the entire thing. Because linear elastic analysis back calculation is, you saw it, it's an Python code, it's an open-ended. You can write a FEM code. Again, there is enough documentation for you to figure it out how to do that. You can write an FEM code and you just say that this is my test result. Apply a 9-kip load or a half of an E cell onto the surface. Calculate the D0s and everything, feed in or feed into the FEM, calculate the D0s, automatically feed into the back calculation, automatically do like a scalar and stuff like that, and now find out E1, E2, E3. That's a pretty cool tool for you to go to the Morse or somebody and say that, look, now if somebody test data of resilient can give you a single modulus, which is very representative of that length. Do you understand? There is no garbage of assumptions. There is no 1500 CBR. It is purely mechanistic. You're basically doing a mechanical. I think with somebody with some decent programming background, I don't think this will take more than a year. You can finish this. So anybody, all the get it done. Not very difficult. I can't do it because, you know, in America I have to pay students, right? The government does not pay me, right? I have to get research for money to pay them. So unless an agency actually wants to do it, I don't want a student to do this. Otherwise, it's very doable. Is this clear what we did? What is the concept of representative modulus? I think we should move on from modulus now. We have spent some time, quite enough time. Yes, K and N, you can do Uzan modulus. I don't think you can. I think you can do MEPDG. I don't remember. We can take a look. You have Uzan model and stuff, so you can do. Sounds good. Okay, let's move on. Okay. So revisit MR models, we did that. Significance of the middle model parameters, we did that. Separate model versus universal model, we did that already, right? I told you this, why they merged this and stuff. There are a couple of papers I really want you to read, okay? One of them, and both of them were shared with you yesterday. I just want to highlight those to you. There is a state of the art paper. Again, it's not state of the art anymore because it is a 2001 paper, but it's a very well written paper by Lecarp et al. On resilient modulus of unbound aggregates. Okay, and it gives a lot of details about how the models work, how the moving wheel load should be captured, what is the difference between constant confining versus variable confining, what are the effects of moisture content, what are the effect of aggregate type, what is the effect of low stress history, load duration, computational modeling, how it is done, how the different models are developed, where are the parameters coming from. There's a lot more models that we thought about and whatnot. So it's a very good read, and anybody claiming to be doing unbound aggregate research should not go without reading this paper multiple times. It's a very good, excellent paper on this. And when we are on the topic, although you don't know anything about deformation yet, I'll show you on the same year they published another paper called State of the Art 2, which is called Permanent Strain Response. And I've shared this with you as well. So it's one is resilient modulus, one is permanent deformation. Excellent papers. You should definitely read them if you want to have a good background of these concepts. Okay, let's keep going. Oh yeah, another one. Oh, crap, I forgot. Another one. Again, I think this was sent to you as well last night when I was sending emails at ungodly hours. This is a literature review report that Errol Tutumler wrote when he was a postdoc. I heard he was just starting and stuff. It's called Granular Material and Soil Moduli Review of Literature. Again, it goes into all the models of resilient modulus and it discusses the details of them. What are the significant parameters? How were they developed? What are the what are the advantages, what are the disadvantages and stuff like that. So again, if you want to write a literature review on this kind of thing, this is giving you 80%, 70% of the information. Excellent, excellent reference. I shared this with you as well. So again, read this again. I hope so, because we are now coming down to the ending part of this workshop, right? Half more day left today and then less you tomorrow. There's going to be some more philosophy than just technical talk, right? Don't do research without reading literature, right? Don't ever do that. At least every research, at least in my group, I encourage that every single work day of yours should have at least 4 to 5 hours of pure reading. No testing, no data analysis, reading, right? The more you read, the more ideas you'll get, the better your knowledge is going to be, the better prepared you will feel something. Otherwise, essentially what's going to happen is you come up with a brilliant idea, go to your advisor, and the advisor is like, yeah, they did it back in 2015. You just haven't read enough, right? So reading is very, very important. So please make sure you get enough reading done if you are into research line and stuff.